Hello and welcome to my new lecture where I'm going to show you the first major chapter in learning of electric machinery. So the first chapter of learning electrical machines are magnetic circuits. Now you see the title of my video is Magnetic Circuit 1 IH-BH relation. In this course I'm gonna do the theory of magnetic circuits and I'm gonna do the example. So when I'm going to do an example, it's gonna say on the title magnetic circuit for example number 1, magnetic circuit 5, example number 2. You will see that there are theory and practice problems and examples in this course. So when I finish this course, I'm gonna make a playlist, and it depends from what time you are looking this video. If I finish the complete course, I'm gonna make the playlist and I'm gonna show it in the description. So look at my description. If I did the whole course, you will be able to see the whole playlist of this chapter in magnetic electrical machinery. So let's start with the lecture. So if we have, for example, a conductor carrying current like so, and it shows up, then around that conductor are going to be formed some magnetic quantities that are called magnetic field intensity and magnetic flux intensity. This magnetic flux density is this vector B, or this quantity B, is usually called magnetic flux density, but there is another terminology that says that this is called magnetic induction. So these two quantities, physical quantities, are called are vectors, and they are in the same direction in the linear mediums. If you learned electrical engineering, fundamentals of electrical engineering, there you learned that in some cases that these two quantities are not in the same direction. But in electrical machinery, these two quantities are always in the same direction, because we always study electric machinery with linear mediums. So these two quantities are in the same direction. And if you remember in physics or fundamentals of electrical engineering, first you learned the Biot-Savart's law. I did. And we first studied that I produces B, and then later on we studied that when we have B, then we will have H, capital H. But here in electric machinery, it is more flexible if you first study this IH relation. So when we have a current going upwards, then we are going to have magnetic field intensity around that circle. So the direction, how do you know the direction of this magnetic field intensity? Well, the right hand rule. This right hand thumb shows the direction of the current, and these other fingers show the direction of the magnetic field intensity. And yeah, that's kind of it. So this is the IH relation. Don't look this big. Now, if we have a closed loop like here, it can be, it depends on what kind of material are you working with. It can be what kind of closed loop you want. we can measure the magnetic field intensity if we know all the currents that go into the or out into this closed loop or out of it, or out of that closed loop. And we can do it with the Ampere's circuit law, which says that the closed loop integral of the multiplication of H and dl is gonna be equal to the sum of all the currents that go through that closed loop. And in this particular example, it is equal to I1 plus I2 minus I3. How do you know that? Well, look, this H shows that the vector of magnetic field intensity is going towards this whiteboard, and this currents go upward and downwards. So how do we know if it is plus or minus sign? Well, we take the right hand rule, and if we show if the current is going like this, then the magnetic field density are supposed to go like this in this direction, counterclockwise. And if the H, this vector H, if we assume that it's going towards the whiteboard, then we take the positive sign. And I1 plus I2 produces a magnetic field intensity that is which direction is at the whiteboard. If we have I3 that goes in other direction, the magnetic field intensity of I3 is going to show in the opposite direction of this vector H. So we take the minus sign in front of I3. Now, this here is multiplication of two vectors, which gives us a scalar. Scalar is, how do you do it? Well, when you get a scalar from multiplying two vectors, you then get the intensity or the length of these vectors times the cosine of the angle between those vectors. So this dl is the direction of the closed path, and here it is really, really small. So small it goes to infinity. Really small, so 0 point infinity number of zeros, and then you have number 1. And it shows in this path, at this moment, the dl shows in this direction, but the vector magnetic field intensity shows in this direction, towards the whiteboard. So you have H dl cosine of theta is equal to sum of the currents that go into that closed loop, and of course the integral of this closed loop. So now here we have an example of one closed path. This is a circle. It isn't a perfect circle, but let's say it is a circle. Now, if we have a current that goes through that circle upwards, then we will have the magnetic field intensity going towards the whiteboard. That is why I put this circle and an X in it, so that it says that this vector is showing towards the whiteboard. So, if we take the right hand rule, this thumb shows the direction of the current, and these fingers show the direction of the magnetic field intensity, then we can calculate what is magnetic field density, what is the quantity of this, what is the formula for magnetic field intensity. Okay, so we put here the Ampere's circuit law. Let me just say that dl and H in a circle are always in the same direction in a circle, so you don't have to worry about this cosine theta is equal to 1, because the angle between this DL and H is always 0, and we will take that cosine of 0 is equal to 1. Okay, so now we have a constant that we can pull out of the integral, and we have integral of the closed loop by dl. This is a simple integral. The intervals are from 0 to 2πr. It starts here, makes the circumference of the circle, and the length of that circumference is 2πr. R is the radius of the circle. So when you do this integral, it's very easy. You get h times 2πr is equal to I. Or we have only one current that goes into the circle, or sorry, through the circle, and then we get the magnetic field intensity is equal to the current divided by 2πr. So this is a situation when we have a closed loop that is in shape of a circle. So that's how we calculate the magnetic field intensity when we have a circle. So that's kind of the story of the magnetic field intensity. But another quantity, magnetic flux density, is also very important. And when you have magnetic field intensity, no matter where you are, you will always have the magnetic flux density. And these are the formulas for the magnetic flux density. So this is called the BH relation, the relation between this and this. So here you have the formula. B, magnetic flux density, is also a vector, and this, because we are gonna learn magnetic circuits, and this we're gonna calculate the magnetic field fluxes, density of fluxes in linear mediums. For example, air gap is a linear medium. Air is a linear medium, and ferromagnetic materials, which are the most common in electrical machines, are also linear. So we don't have to worry about the directions between this and this, because they're always in the same direction. And this is equal to mu times h, and mu is equal to mu 0 times mu r, and these are called this mu is called the permeability of the medium. That's a kind of a physical quantity that is experimentally calculated. Mu 0 is a permeability of free space. When I say free space, it's usually a vacuum, or it's a vacuum, and it's not quite right to say it's air, but it's air. So free space is vacuum and air, and mu r is the relative permeability of the medium. So this mu 0 has a quantity of 4p 10 to the minus 7, and this mu r, and it has its own unit, Henry per meter, and mu r is the relative permeability of the medium, and it has only a number, for example 200. It doesn't have any unit to itself. So this is the formula for the magnetic flux density, when you know what is the magnetic field intensity, and these vectors cancel when you have the linear mediums, when the direction of these two is the same. Fortunately for us, we are going to learn only those mediums where these two are the same. In physics or fundamentals of electrical engineering, there are materials you learn that are not that these quantities are not in the same direction. But in electric machinery, fortunately for us, we are going to learn only those materials where these two are in the same direction. So that kind of makes stuff a lot easier. Thank you for the attention, and see you in my next video where I'm going to do another theory called the magnetic equivalent circuit. You will see what it is. Maybe I'm gonna do the third video also a theory, and I think the fourth video of this course is going to be an example. Thanks for watching and see you in my next video.